Imagine you are a programmer. You have been given a task. Build a universe. Not a model of a universe. Not a simulation for scientific purposes. An actual universe. One that contains matter, energy, space, time, and eventually conscious beings who will try to figure out what they are living inside. You sit down and you start writing the rules, the laws that govern how everything behaves, and immediately you face a practical problem. The universe you are building is going to be incomprehensibly large. It is going to contain more particles than you can track individually. More interactions per second than any system you could build could process one at a time. The computational cost of running a true particle-by-particle simulation of an entire universe from the beginning of time to the present would be infinite. No system could do it, not even in principle. So you make a design decision. You don't render everything. You only render what is being observed. Everything else you leave in a state of unresolved possibility, a superposition of all the outcomes it could have, until something inside the simulation looks at it. At that point, you resolve it. You commit to one outcome. You render the detail, and then you move on. This would be the most computationally efficient way to run a universe. Render on demand. Resolve only what is observed. Leave everything else in superposition until it needs to be definite. Now open a quantum mechanics textbook to any page. What you will find is a description of exactly this. A universe in which particles have no definite position, no definite momentum, no definite state of any kind until they are observed. A universe in which unobserved systems exist as superpositions of every possible outcome simultaneously and only collapse to a definite state when measured. A universe that is, at its most fundamental level, indefinite until something looks at it. This is not a philosophical interpretation of quantum mechanics. It is the operational description of what quantum mechanics says happens. The wave function, the mathematical object that describes the state of any quantum system, does not describe a system with a definite but unknown state. It describes a system that genuinely has no definite state until observation forces it to have one. The measurement problem, the question of why and how the wave function collapses, is one of the deepest unresolved questions in physics, precisely because the collapse is so strange. So unlike anything a purely physical system should do. So exactly like what a computational system, resolving an unrendered state, would do. A programmer designing a universe for computational efficiency would build exactly this. And this is exactly what we find. That is the first line of code. And it is far from the last. Let's build the case systematically. Because the simulation hypothesis is not a fringe idea supported by one or two convenient observations. It is a framework that, when you hold it up against the actual features of physical reality, fits with a precision that is either deeply meaningful or the most extraordinary coincidence in the history of human thought. Start with the most fundamental feature of the universe, not space, not time, not matter or energy. The rules themselves, the fundamental constants of physics, the numbers that determine how strong gravity is, how fast light travels, how much mass an electron has, how strongly the fundamental forces interact with each other. These numbers are not derived from anything deeper in our current physics. They are inputs, parameters, values that the universe simply has, that our theories take as given, and that have no explanation within the standard model of particle physics or general relativity. And they are extraordinary, not just in their values individually, but in their relationships to each other. The fundamental constants of physics are tuned to a precision that produces a universe capable of complexity, with an accuracy that defies casual explanation. Change the strength of the strong nuclear force by a few percent, and carbon cannot form in stellar cores. And without carbon, there is no organic chemistry, no life, no observers. Change the cosmological constant, the energy density of empty space, by even a tiny fraction, and the universe either collapses back on itself immediately or expands so fast that matter never has the chance to clump into galaxies and stars. Change the ratio of the electromagnetic force to gravity, and stars either burn out in seconds or never ignite at all. The universe is not just compatible with the existence of complexity and life. It appears to be calibrated for it, fine-tuned to a degree of precision that physicists find difficult to explain by any natural mechanism. The probability of the fundamental constants taking values that permit complexity by random chance is so small that it has driven serious scientists toward extraordinary explanations. The multiverse, the anthropic principle, and yes, deliberate design. A programmer setting the parameters of a universe they wanted to contain conscious observers would set these values. And these are the values we find. Now consider the structure of space itself. At the smallest scales, scales far below anything we have directly observed, at the Planck length of approximately 1.616 times 10 to the minus 35 meters, space appears to have a minimum meaningful unit, a smallest possible distance below which the concept of distance loses its meaning. Our physics does not describe what happens below the Planck scale. The equations break down. The predictions become undefined. The framework that successfully describes everything above this scale simply stops working below it. This is either a fundamental feature of the fabric of reality, or it is a resolution limit, the smallest unit of space in a simulation that was built with a finite resolution, a pixel size, below which there is no detail because no detail was rendered. The same applies to time. The Planck time, approximately 5.39 times 10 to the minus 44 seconds, is the smallest meaningful unit of time, the shortest duration below which the concept of temporal sequence loses its meaning. Below this threshold, our physics produces infinities and contradictions rather than predictions. Either the universe has a fundamental temporal granularity, or it has a minimum time step. The frame rate of the simulation. Consider the speed of light, the maximum speed at which anything can travel through space, the hard upper limit on the transfer of information across the universe. Nothing exceeds it. Nothing reaches it except massless particles traveling through vacuum. It is not just a property of light. It is a property of space-time itself. The geometry of relativity is built around it. It is the most absolute limit in all of physics. A natural universe has no obvious reason to have a maximum speed. Matter and energy moving through space do not self-evidently require an upper bound on their velocity. The speed of light is not derived from anything more fundamental in our current understanding. It is a parameter, a value that the universe has. But a computational system has a natural reason to have a maximum information transfer rate. The speed of light in the simulation framework is the bandwidth limit, the maximum rate at which information can propagate through the computational substrate. Not a law of nature imposed from outside, a constraint imposed by the processing architecture from within. Every calculation the universe performs, every particle interaction, every gravitational attraction, every quantum event is bounded by this limit. Nothing in the universe can do physics faster than light allows. That is either a coincidence of natural law or a feature of the system's architecture. Now consider something more abstract but more profound: the unreasonable effectiveness of mathematics. In 1960, physicist Eugene Wigner published an essay with that title that has never been adequately answered. The observation is simple. The universe is described by mathematics, not approximately, not roughly, with extraordinary, unreasonable, inexplicable precision. The equations of quantum electrodynamics predict the magnetic moment of the electron to 14 decimal places. The predictions of general relativity have been confirmed to similar precision in every test ever attempted. The standard model of particle physics, despite its known incompleteness, has produced predictions confirmed to degrees of accuracy that no other scientific framework in history approaches. Why should this be true? Why should the universe, a physical system that evolved without reference to human mathematics, be describable by mathematical structures that humans developed through abstract reasoning? Mathematics was not designed to describe physical reality. It was developed through pure logical reasoning, following internal consistency rather than empirical observation. And yet it fits perfectly, universally, at every scale from the quantum to the cosmological. There is no satisfying answer to this from within the framework of a purely physical universe. If the universe is a physical system that simply exists, there is no reason its behavior should correspond to abstract mathematical structures with this degree of precision. The effectiveness of mathematics in describing physical reality is, as Wigner said, unreasonable. But if the universe is a computational system, if it is built from mathematical rules, if the code that runs it is mathematics, then the effectiveness of mathematics in describing physical reality is not mysterious at all. It is expected. You would expect the programming language to describe the program with perfect precision, because the program is written in that language, because the universe is not described by mathematics. It is mathematics running. This is the position of physicist Max Tegmark's mathematical universe hypothesis. Not that the universe is like a mathematical structure, that the universe is a mathematical structure, that physical existence and mathematical existence are the same thing, that the reason mathematics describes reality so well is that reality is mathematics and has always been mathematics, and the only thing that was ever here was the abstract logical structure that we have been slowly discovering and calling physics. If Tegmark is right, and his position is controversial but not dismissible, then the source code of the universe is not something hidden beneath physical reality. It is physical reality. The laws of physics are the code. The constants are the parameters. The particles are the data types. And the universe is a program that has been running itself for 13.8 billion years. Now here is where the case becomes most interesting, because the simulation hypothesis makes a prediction that the physical universe hypothesis does not. If the universe is a computational system, it should have the features of a computational system: discrete units, maximum processing speeds, render on demand, parameter inputs, mathematical substrate. And when you look at the actual features of the universe, quantization, Planck scale granularity, the speed of light, quantum superposition, fine-tuning, the mathematical structure of physical law, you find exactly those features, every one of them, not approximately, not suggestively, precisely. This does not prove the universe is a simulation. Proof is not available from inside the system. A simulation sophisticated enough to be convincing would be indistinguishable from a physical universe by any measurement made from within it. The test cannot be run from the inside. And the alternative explanations, the multiverse accounting for fine-tuning, the Planck scale as genuine physical granularity rather than resolution limit, the speed of light as natural law rather than bandwidth, are all serious and all deserve consideration. But here is the honest position. The simulation hypothesis is not a fringe idea. It is a framework that fits the evidence with a precision that alternative explanations have struggled to match. It was taken seriously by John Wheeler, who believed information was more fundamental than matter. It has been explored seriously by physicists, including Tegmark, by philosophers, including Nick Bostrom, whose simulation argument remains one of the most discussed papers in academic philosophy, and by scientists across multiple disciplines who find the fit between computational architecture and physical reality too precise to ignore. The evidence has been there all along, in the structure of quantum mechanics, in the Planck scale, in the speed of light, in the fine-tuned constants, in the unreasonable effectiveness of mathematics. Each one individually has alternative explanations. Together, they form a pattern that points consistently in one direction. And the direction they point is not toward a universe that happens to resemble a simulation. It is toward a universe that behaves, at every level of analysis, exactly like one. If you are the kind of person who finds that the most interesting questions are the ones where the evidence keeps pointing somewhere uncomfortable, where following the data leads to a conclusion that changes what you think you are living inside, then Cosmora is exactly where those questions live. Subscribe and stay. The catalog goes deeper from here, but before we close here is the thought that belongs to you now. Every law of physics you have ever learned, every constant you have ever seen in an equation, every rule that governs how matter moves, how energy flows, how time passes, how space curves, every feature of the universe that makes it what it is, all of it fits on a list. A finite list of parameters, rules, and mathematical relationships that completely describe the behavior of everything that exists. From the largest galaxy cluster to the smallest quantum fluctuation. From the first fraction of a second after the Big Bang to the last evaporation of the last black hole. A finite list of rules that governs an infinite universe. Rules precise enough to produce stars and planets and oceans and life and minds capable of asking what the rules are. That list exists. We have most of it. We call it physics. But there is another word for a finite list of rules that governs the behavior of a complex system. We call it code. And somewhere, inside the mathematics, beneath the physics, at the level of reality that no instrument has yet reached and no theory has yet fully described, the source code is running, has always been running, will continue running until the last computation completes and the final output resolves. Whether anyone wrote it is the question that lives beyond the evidence. But that it is running, that the universe operates exactly like a system that is running, is something the evidence has been telling us for 100 years. We just had to learn to read it.